This is rotation vectors. I'm going to show you how rotation vectors are used and go to rotations and translations. Hopefully we can get there. So today's class, part of today's class is rotation of a vector in coordinate frame. So this is very central to this course because we'll keep having rotations of frames and vectors. So let me illustrate this with a picture. What we have is there is a point. Let's say that right now it's on the x-axis, along the x-axis. So this point is P, and I'll call this frame OO, XO, YO. Okay, what's going to happen is I'm going to rotate this frame. So just redo that frame as a reference. We'll show the rotated frame. Okay, so all rotations counterclockwise are positive. So when you rotate this vector, it'll end up at a new point here. Okay, so this vector is called P0. Remember our notation, you put P, small p, for the vector, and then you put 0 to indicate it's in frame. It's in frame 0. The vector in frame 1 is P1. Again, to remind you, the position of P in frame 0 is going to be 1, 0. That's because it's along, not 1, whatever that magnitude is. If it's x, then if this length of the vector is, let me give a better name to it. Let me call it, let's say, capital P. I just drew the bar to show that it's capital P. So the length is, so you'll call it P, comma 0, right? When you rotate it and you want to find P1, okay, in frame 1, it's still going to be P, comma 0. Why? It's because this vector is now measured in frame 1, and so it's still 1 P units along the x1 axis. So that what I've written down is its length on the x01, x1, y1 frame. Okay, so it's the same. It looks like the same value, but it's really different because that P, comma 0 is in frame 1, O1, x1, y1, and that P, first P, is with respect to frame 0. So if you want to find the position of point P in frame 0, not frame 1, in the new position, so this coordinate, then clearly this is P sine theta. Let me just write this down as, this is a scalar, so there's no confusion. And then let me write the x coordinate. Right? It's P cosine, P sine. That is the coordinate of point P in the new. So this point P now, this point is going to be P cosine theta for the x and P sine theta for the y. Right? Because I just use trig to do that. Now, what we don't want to do is we don't want to keep drawing these frames and figuring out from trig, and so this is where the rotation matrix will help us. So what I'm going to do is I'm going to show you how to use the rotation matrix which we defined in the last class to get this coordinate. So okay, so my claim is that P0, the position of point P in the rotated frame, well, now this P denotes this point. Okay, it's not denoting the first point. The first instant is when it starts off, when it rotates, and so this P has now moved to over here, and this is what I claim. And then what we'll do is we will check this. Okay, so let's write down the rotation matrix. It's cosine theta, and this comes from our last lecture where I defined the rotation matrix. Okay, and P1 is the P over there, so it's going to be P along the x-axis and 0 on the y-axis. So if you do this multiplication, right, if it will be cosine times P minus sine times 0, then sine times P plus cosine times 0, you'll get P cosine theta, P sine theta. So what you see is you get the same, we get this, right? We get exactly what we got using trig. So what I'm trying to say is that instead of doing trig, we'll always use this transformation to relate one vector with, try to find the position of vector in the rotated frame with respect to the original frame. So that's the formula which we'll be using. So this is something to remember. In fact, this will be used again and again. So where this is useful is when we'll talk about multiple rotations. We just did one rotation. What happens if there's two rotations? Okay, so consider rotation of a vector P from frame OOXOYO to O1X1Y1 to O2X2Y2, and you can keep going all the way to n rotations. Okay, the vector has length P0, P1, and P2. This is our definition. In frames O, OOXO, YO, O1, X1, Y1, O2, X2, Y2, respectively. Okay, what we have seen is P0 is R10 P1. Okay, that's a formula which we wrote down, right? But that same formula is also true for the second rotation. Just like you can go from 0 to 1, we went from 1 to 2, and that corresponding rotation matrix is R. So we want to find the rotation matrix from frame 2 to 0, because we end up in frame 2 and we start with frame 0. So what we are after is, what is that R to 0 which will relate frame 2 with frame 0, or the position of vector P from frame 0 all the way to 2. So we are after R to 0. So what you can do is you can take the equation 1 and 2 from 1 and 2. We can sub in the value for P1, take this P1, put it there, and we get P0 equals R10, R21, P2. So now if we compare 3 with 4, we get R20 is simply R10 times R21. Okay, so what you got to remember is, if you want to find the rotation matrix of frame 0 with all the way to 2, it's first the rotation matrix of frame 0 with 1 times rotation matrix of 2 with respect to frame 1. So you can then go from Rn to 0 by keep doing 1, 0, 2, 1, n it be 1, 0, 2, 1, 3, 2, and so on till n minus 1. Okay, so what I'm going to do is I'm going to illustrate this with a problem. Okay, what does this really mean? What does this rotation matrix mean? And I'm going to do a graphical illustration of that, really. You got to add this. Okay, if R represents rotation by an angle phi about current y-axis, followed by rotation by an angle of theta about current z-axis, then find R. So what's going on is something like this. So this is a three-dimensional rotation because you're rotating about different axes. So let's start off with frame 0. So 0, 0, x 0, y0, z0. Now you're going to be careful when you do these rotations. Remember the right-hand rule. Always draw x and y axis such that when you take your right hand and you curl your fingers from x to y, you get z, because that is the right-hand rule. You can't use your left hand because then it's a different convention. So I drew that so that it follows that. X comma y should, if you do x comma y, your thumb should give z, and if you do y comma z, you should get x, and z comma x, you should get y. When I say that z0 actually points out of the plane of the paper. Okay, so given that, what I'm saying here is that rotate by phi about current y-axis. What's going on is you're going to turn the vector about the y-axis. So when you turn the frame about y-axis, so you will turn so this way. Okay, can you imagine it? Actually, the coordinate frame is turned like this. When you turn it, this angle would be phi, and this will be phi. So when you turn this will become z1, x1. But since you're rotating about the y-axis will not rotate. It will, by that I mean it will be along the same direction. So y1 is along y0. So that's step 1. Let's do step 2. It's best if I eliminate some drawings over here. Let me copy. Okay, so I'm going to get rid of x, x0, y0. Okay, and next rotation is, it's saying rotate by an angle of theta about current z-axis. What it means to be current z-axis is the new z-axis. The new z-axis is z1. So what we do is we rotate about the by an angle of theta about the z-axis. So what that will do is it would lead to something like this. So this is turned. Again, this is the turning is always counterclockwise. That's theta. So this is going to be theta. This is going to be theta. So x2, y2. Since you're rotating about the z-axis, that will be unchanged. So that's what is going on. Okay. A better way is to illustrate this is if you have your phone and if you want to think of x, let's see. Yeah, say x is this, y is that. Let's do x is this, y is that. So x comma y is z. And so first you rotate about the y-axis. So this is my y-axis. So I'll rotate about y-axis, say 90 degrees. Now when you rotate about the y-axis, you have your new y-axis will still be this, but your x will be still along that. But remember, x was this way, turned that way, and the z would be 90 degrees. So then you turn about the z-axis, so you turn this way. That's what it means when I do those rotations. So here the question is find r. So r is, so that you don't have to do that all the time unless I ask you, but r is going to be rotation about, first you're going to rotate about y-axis about an angle phi, and then we're going to rotate about the z-axis by an angle theta. So that's what you would do, and this comes from what we did last time. Well, by that I mean what we did just a while back, this rotation. When you want to find rotation about frame 2 to, from frame 0 to 2, you first do the rotation. The first rotation comes first, the second rotation comes later. You cannot switch the order. It's very important. You don't switch the order. First followed by second. We did the same thing here. The first one, then we did the second one. Okay, and so what remains is to write down the formula for r, y, phi, and r, z, theta. So this is something which I wrote down in my last class, 0, s, phi, and you can just copy it down. And then do the multiplication. So c theta minus s theta 0, s theta c theta 0, 0, 0, 1. And then, well, let me write what c and s is. This is cosine of phi, s theta is sine of theta, and so on. So when you do this multiplication, you get c phi c theta minus c phi s theta s phi s theta c theta 0 minus s phi c theta s phi s theta c phi. Okay, so that's the answer. That is what you would get if you do two rotations. Clearly, it looks much complicated than the simple things, but these are building blocks. So if you can decompose any rotation about the x, y, z, then you can multiply this. You don't have to remember this. What is important is that you remember these individuals. You don't have to remember in this case because it's a take-home exam. You just have to know how to write these things down. Okay. Now let's do an exercise. Let's switch the order of rotations. What I've done here is, my problem was rotate about the y and then z. So first y, then z. So the next problem is, we'll reverse the rotation. If the above rotation order is reversed, okay, that is, if r represents rotation by angle phi about the current z-axis, followed by angle theta about the current y-axis. All we did was we do the same rotations phi and theta, but first one is about z. Earlier it was about y, and then we do about y. So now for this one, you can draw the same picture if you want to. If I ask you, you should do it in the homework. But I'm just going to write the formula and write the final answer. So in this case, r prime is first. Again, you go by the formula first, rotation first. So z phi times y theta, right? It was r21 is r10 times r21. I'm just following that first times second. So now let's expand this out. C theta minus S theta 0, S theta, C theta 0, 0, 0, 1, C phi 0, S phi 0, 1, 0, minus S phi 0, C phi, and a little bit of math. In fact, you can use the symbolic toolbox, which I showed in the second class. You can easily do this using MATLAB. It comes out to be S theta, C theta, S phi, S theta, C phi, C theta, S theta, S phi, minus S phi, 0, C phi. Okay, let's compare this with what we got earlier. I'm going to copy paste my earlier answer. Okay, again, the difference between the two problems was, in the first one I rotated first about y and then about z. In this case I rotated about the z first and then about y, right? So this is what I have for second one. The first one was r y phi times r z phi. We see that r is not equal to r prime. Okay, so when you do these rotations in reverse, you don't get the same answer. And that's very important, that the rotations are not commutative. Commutative is when you do a times b is the same as b times a. If you multiply two numbers, that's true, right? 2 times 3 is same as 3 times 2. If you do rotations about axes, they do not commute. And actually, you might say, why? Well, is this really true? And I can actually illustrate this with, we can do the same exercise with my phone. We can fix axes and do 90 degrees rotations, and I'll show you that it's actually true. So let's do the same exercise, okay, with my phone. We have to remember a few things. Always, I'm going to assume that x is along the inner edge of my phone, this way. Y is along the shorter axis, and then x cross y is z, so z is that way. Okay, so first we rotate about 90 degrees about the y-axis. Is that right? Let me check that. Okay, x, y, and z. 90 degrees about the y-axis. Y is there. 90 degrees about y. So I need to curl 90 degrees, so I go this way. Now I need to do 90 degrees about the z-axis. So, but let's first see what happens to the x, y, z. X is still this way. This is the new x. This is the new y. And then the new z is this way. It actually is always going to be x, y, and z, no matter how you rotate. That's the convention. So now we do 90 degrees rotation about the z-axis. The z-axis is this way, so I do 90 degrees about z. So I call it like this. So the phone is this way. So I started this way, and I ended up this way. Okay, where my screen screen was up, now screen is to the right. Let's do the same rotations, reverse the order of rotations. Let's start off same way, X, Y, and Z. So first is 90 degrees about the Z axis. So Z is upwards, so 90 degrees about Z, so go this way. So again, X will be that way, Y, and Z is upwards. 90 degrees about the Y axis, so I said Y is this. So I turn 190 degrees about Y, end up that way. Okay, so I start this way, end up this way in the second one, and the other one I ended up that way. So clearly you can see that rotations are not commutative. I'll repeat that again, okay, and you should try this yourself. In fact, the way I actually do it is using an aeroplane. You can see that if you do change once, it ends up upside down, once it ends up, and that's really can be catastrophic because if you do not have the right angles, if you mess up your angles, then you'll actually crash the plane, right? So let's start off again. X along this, Y along that, Z up. First rotate about 90 degrees about the Y axis. Y is there. Rotate 90 degrees this way. Then 90 degrees about the Z axis. Z axis always points outward. 90 degrees this way. So start this way, you get that way using the first example. Again, let's do the second one where we do first about the Z axis. So Z is upward, 90 degrees about Z, and there. And then we do 90 degrees about the Y axis, so Y is always, okay? We end up that way. So start off this way, we end up this way for the first example, and we end up that way for the second one. Okay, you should try this out. It's like fun exercise to do. Any questions on that? Questions? So I'm going to write here that rotation matrices do not commute. Okay, so we can we can do a lot of rotations. We don't have to restrict to 2 rotations. So sometimes it's more meaningful to have 4 rotations fine. So here's an example which is asking for finding the rotation matrix when there are multiple rotations. Okay, so we define R through the following stepwise rotations. First rotation about alpha about current X, beta about current Z, gamma about current Y, and then small delta about current X. What's the rotation matrix? So what you would do is, in this case, if you would like, you can build it stepwise. So 1, R would have only X alpha, right? Step 2, so I'm trying to build R stepwise fashion, so it's easier. When I do the next multiplication, again, as I said, do not commute. You cannot have it any way, but only one way, which is you post multiply about the next rotation, so Z comma beta. Third one would be R equals Rx alpha R Z beta, and the third one is y-axis by an angle gamma. And then fourth one, and this is actually our final answer, x comma alpha Z comma beta y comma gamma times R x comma small delta. So that is the final answer, but I showed you how to build it stepwise fashion. Once you have this, it's very easy to do it in MATLAB. In fact, I typically write functions for x, rotation about x, rotation about y, and rotation about z, and then just call that function to build that matrix. Unless asked, you don't need to actually do this multiplication and put in the answer. In fact, this multiplication, if you put it, it's going to be huge symbolically. If you put values to alpha, beta, gamma, and delta, it will actually be just a 3 by 3 matrix. Okay, clear? Okay, so next we'll talk about rotation, parameterization of rigid body rotation. Okay, so what I mean by parameterization? Parameterization of in a way, parameterization is about finding the minimum number of variables to describe a given uh, uh, formula. So the simplest thing, and if this might be something you've done before, is how do you parameterize a parabola? So parabola is, so parameterization example. So you have a parabola, y equals x squared, and one way to describe any point on the parabola is describe any point on the parabola as, well, it would be, if you use t as the parameter, then t for x, t square of the y, so t is the parameter. What it's saying is that as t is varied, in this case minus infinity to plus infinity, you'll be able to generate the curve. So for each so t will go from minus infinity to plus infinity, and you'll get t squared in the y-axis. Okay. Another example would be, how do you describe a circle? Now for a circle, which is x squared plus y squared equals, let's say, r squared, there's one parameter, you can use theta, so x equals r cosine, or let me write it this way, r cosine theta, r sine theta is how you describe any point on the curve, on the circle. Okay, so you can use one variable theta to describe the curve, where theta goes all the way from 0 to 2 pi. Okay, so it's the simplest way to describe an equation is, one way to do it is parameterization. So in case of rigid body rotation, the question is, how many numbers do you need to describe the rotation of an object? So if you start, it moves, how many numbers do you need? Do you need one number, two numbers, 10 numbers? And the best way to think about this is to think of the rotation matrix. Okay, when you rotate about x, y, z, whatever you like, you'd end up with a rotation matrix. That rotation matrix would have terms like this. Which means eventually end up with 9 numbers. So the question is, do you need 9 numbers to describe rotation? So the answer is no. You do not need 9 numbers. In fact, all these numbers which in the rotation matrix are not independent. Okay, rotation matrix is a special property, which is it has what is known as norm of 1. That is, when you do r times r transpose, it should give you I. Because when you rotate a vector, that vector, so when you take the rotation matrix, multiply the vector, it rotates, right? The rotation matrix shouldn't scale the vector by, it shouldn't increase the length or decrease the length. So that requires the rotation matrix to have a certain property. The property is that r transpose is I. So this actually imposes a constraint on the 9 numbers, and the 9 numbers have certain relations they have to follow. So this constrains the 9 numbers. Okay, so if you take this particular expression and you put the r I drew there, r, those 9 numbers, you multiply, you'll get this 9 constraints. Sorry, you'll get the 6 constraints. These constraints are R11, square plus r21 square plus r31 square equals 1, r12 square plus r22 square plus r32 square equals 1, r13 square plus r23 square plus r33 square equals 1. And that actually comes from the diagonal. When you do this expansion, the diagonal has ones that comes from the diagonal. And then there are other constraints which comes from the non-diagonal elements. And those constraints are r11, r12 plus r21, r22 plus r31, r32 equals 0. There are two more, r12, r13 plus r22, r23 plus r32, r3 3 equals 0, and then r13, r11 plus r23, r21 plus r33, r31 equals 0. So these are 6 conditions. 6. Okay, these are constraints on the matrix. So 9 numbers minus 6 constraints, we left with 3. So there are only 3 unique numbers or parameters needed to describe rotation. Okay, just 3 numbers, and those 3 numbers could be rotation about 3 axes. So we have rotation about x, y, z. That is just one way of representing a rotation. You could have rotation about x, y, x. That's another way. You could have z, y, x. You could have, so let's just list all the various ways you can. So what we'll do is, just like a circle, you have one theta. For rotations, we will use 3 angles, and that's the normal way to do it. We will use 3 rotations to parameterize rotations. Okay, and as I said, those could be anything. Yeah. Sure.
How did you get the last 3 conditions?
Those conditions come from looking at this matrix. It has 1, 0, 0, 0, 1, 0, 0, 0, 1. And so if you compare the diagonal elements, you get these 3 conditions. And if you look at the off diagonal element, this one, this one, this one, you get 3 conditions. But this one, this one, this one gives you the same 3 conditions. And so you only end up with 3, not 6. Okay. And you can check this with the symbolic toolbox. Is that okay? Okay, so there are 12. So how do you describe rotations? When I rotate an object, there are 12 ways to describe rotations, because there are 3 angles, and those 3 angles can be combined in multiple ways. So 12 representations, and they are x, y, z, x, z, y, x, y, x, x, z, x, y, z, x. So when I say y, z, x, really rotations about y, rotation about z, and rotation about x, by a predefined whatever angle you want to rotate them. X, y, y, z, y, z, x, y, z, y, x, z, y, z, and then z, x, z. Okay, which means that if you rotate this cup, it ends from here to a different angle, you can find 3 rotations about any of these frames. And now clearly it's like you end up from this frame to this frame, or this rotation, you could, in a way, describe it by, when you say describe it by these 12 ways, it really means it's like a cup is a cup. You can call it something in English, something in Spanish, something in Portuguese, and so on, but still a cup. So it will give you the same rotation, but it will be a different way of talking about that. And so what people do normally is they don't use all the conventions, it's too confusing. They actually only stick with, there are some popular combinations. So I think this one, I believe this one is called, I think it's called Euler angles. So if you read a paper and they say Euler angles, they actually mean rotation about x, y, z in that order. There's something called Bryant angles, I think, which is z by x. I'm not too sure, so I will not write it down. But there are only some of these which are followed. So when you're talking with somebody and when you see that you get different rotation matrices, do not be surprised. It's because you have used a different convention. And so it's very important to say what convention you use, because we've seen that rotation matrices don't commute, so you have to be very careful. Okay, so this is, we are not going to do too much three-dimensional stuff in the traditional way. We're going to do something called DH for manipulators. But if you're doing three-dimensional rotations, they actually are pretty hard to, it's easy to run translation. So I'll first define what I'm going to talk about, which is translation and rotation, and then I'll show you how to represent mathematically the rotation and translation. Okay, so here is what's going on. Let's take the same caricatures as earlier. We have coordinate frame O, X, O, Y, O. Okay, and let's look at point. I'm looking at points. Eventually, we'll talk about, this is planar to give you an idea, but eventually you can do the same thing with 3D objects. So what we do is we want to translate. So what we do literally is move the point, the vector OOPO, to a different point in space. So that's translation. And then we continue with rotation. So we've rotated by theta, and there's translation. Let's call it dx and dy. So the first operation is translation. The second operation is rotation. Okay, so the way you describe the point P now is you first translate. So this is D10, and then I should put our frames, so it's complete. And this is the new X1, Y1 frame. And so first you translate like I've shown. And again, I'm following the same convention. This is translate to frame 1, and this is with respect to frame 0. Plus, we have the rotation part, R1, 0, P1. Okay, so the addition is, because we've seen that, we just added a translation to it. Okay, so we did that to go from frame OOXOYO to O1, X1, Y1. Okay, we can do the same step and go from frame 1 to frame 2. So this should be P2. So I wrote the formula is exactly like it was previously, except I replaced zeros with ones and ones with 2. This is O1, X1, Y1 to O2, X2, Y2. And we are really interested we're not interested in frame 1. We're only interested in the start, which is 0, and the end, which is 2. So I'm going to try to relate 0 with 2, and I don't care about this one. So I'm going to eliminate essentially P1 from 1 and 2. So I'm going to sub in the value of put 2 in 1. I can get P0 equals D10 plus R10. So that was, and there was a P1 here, so that P1 is going to be replaced with D21 plus R21 P0, so P2. I just replaced the P1 from 1 to 2 to 1. So we can we'll simplify this to get D10 plus R10 D21 plus R10 R21 P2. Okay, that looks fairly complicated. So if you want to keep going, that is, this is just rotation from 0 to 1, 1 to 2. What if you want to go from 0 to n frames, theta 1, theta 2, theta 3, so on? Then it will look like this: n rotation, n translations plus rotations. Or the generalized form of this formula would be D10 plus R10 D21 plus R10 R21 P T32 plus so on till you'll end up with R10 R21 so on till Rn n minus 1 D Pn. So it's very complicated. That's the whole point. You have to write a lot of things, right? And it's very messy. So very messy if there are multiple movements, which is translation plus rotation. So what I'm going to show you is there's a very easy way of representing translation and rotations, just like we did rotations. Remember, it was very simple. When we talked about R20, it was just R10 times R21. If you do Rn0, you just have to keep multiplying this rotation matrix, n of those rotation matrix, and it's very compact. So here's a very compact way of representing rotations and translation. It's called a homogeneous transformation. So next part is a compact way of representing rotations and translation is through a homogeneous transformation. Okay, so this is actually the thing which the homogeneous transformation is the trick which will help us to make our life easy when we talk about kinematics of manipulators. And I'll write down the homogeneous matrix and show you how the homogeneous matrix helps us to write those formulas in a very, very compact way. So let's do so this is the last thing. I'll let you go after this. It shouldn't take me too much time. Homogeneous transformation. So let's denote it by H, and H is a matrix. It's the rotation matrix, the translation matrix. Okay, remember that the rotation matrix is 3 times 3, so this might be you might not have been used to this. I wrote that as if it was a scalar, but you can write that because you can you can put matrices within a matrice and it will still be a matrix. So this is 3 times 1 because in generic case we are looking at rotations transition about x, y, z, and then I need to put zeros, and to be compatible this should be 1 times 3. So there are 0, 0, 0 along the row, and then there is 1, and that is 1 comma 1. So the homogeneous matrix is a 4 by 4 entity. A rotation matrix is a 3 by 3 entity. So the way we'll write rotation matrix is, sorry, the homogeneous matrix is R D01. Okay, this is a very compact way. Just instead of trying to write that 4 by 4 and so on. So now here's the best part about using the homogeneous matrix. Remember I had written down P0 as R times P. I can write P equals H times P. So H10 P1. So the same thing as rotation matrix, but I replace it with the 4 by 4 matrix. Then I can write P1 as H21 P2. Okay, so if you put this inside here, you get P0 equals H10 H21 P2. So you see that it's very compact now. Subbing in. Okay, so what's that? Let's expand this out. This is R10 D10 001. I think I'll write it on a new page and to do some math. So P0 is H10 H21 D, so P2. Let's expand it out now. R10 D10 01 R21 D2101, and then P2 is as it is. Let's do the multiplication. Now this is 4 by 4 and 4 by 4, so they're compatible to 4 multiplications. If you do the multiplication, you get R10 R12 R10 D21 plus D10, and then you get 0 and 1 times P2. Okay, so in this particular notation, P is, I just have a sort of abuse of rotation. P is supposed to be 3 numbers, right? X, Y, and Z. In the homogeneous transformation world, you actually need it to append a 1 here. So when you expand it, you really need to put a 1 and 1, and that's just to make this multiplication compatible. Okay. So what I do is I essentially multiply these 2 matrices together and then compare left hand side with right hand side. R10 R12 P2 plus R10 D21 plus D10 01. Okay, so if you compare, you see that P0 is R10 R12 P2 plus R10 D21 plus D10. Let's go back and see what we had got when we used the rotation matrix. So I'm used to copy paste my earlier. Let's copy paste this because we just looked at 2 rotations or 2 movements. Copy. Okay, we see that it's identical, right? So you just switch. This D1 is there. This R1, D2 is right there, and so what we've done is we've found a compact way of representing. You do not need to expand it out. I wouldn't expand it out the way I've done. I just expanded it out to show you how to use the homogeneous matrices and how it compares. So if you want to do something like n rotations, it'll just be H10, H21, H32, so on, H n n minus 1 p n. So that's the formula. I'll end with giving you the transformation matrices for remember now we have, I talked about rotation matrix for 3 rotations, but when there's translation, we have 3 translations too. So there are actually 6 things you need to worry about. So I'll write down one of them, and then you can get the other ones. So if you want to do pure translation, okay, this is actually a homogeneous transformation by an angle A, by distance A along the x-axis. Then it will look like this: 1 0 0 0 1 0 0 0 0. So this is the R part, and then the translation part is A 0 0 0 0 0 1. So similarly, you can write trans y b. I'll complete it later on. Let me write the rotation part. Rotation by x by an angle alpha. So this will also have the first 3 by 3 elements are 0, 0, C alpha, minus S alpha. Exactly the same what we had written down last class. Those 3 are 0, 0, 0 because there's no translation. Okay, and then there is rotation y beta, and then there is translation z c, and then there's rotation z by an angle gamma. I'll complete them down, but we use a similar form. Let me just do one problem and just write a formula and let you go. Just like you had rotations about x, y, z, right? Only rotations. Now you can do rotation, translation, rotation, whatever you want, and it's actually very easy. These are the building blocks, which this I'll fill down a little later, and I'll post my notes. So here's one. I'll end with this problem. Okay, find the homogeneous transformation H that results from the following stepwise transformation: rotation by angle alpha about the current x, translation next about the x, translation d along z, and rotation by angle theta about current g. So I did rotation, translation, whatever way you want. You can actually now build up that transformation going from one frame to another using those 6 numbers. I've not filled them up, but I'll fill them later. This is how it goes. So step 1, you follow the same recipe as rotation matrix. You post multiply. So start with rotation by an angle alpha about x. The second step is rotation by angle alpha. So x alpha is same as it is before, times translation. So you post multiply by x comma b. The third step is you keep the first 2, and then you do translation z comma d, and then the final step, and this is the final answer, is rotation x comma alpha, translation x comma b, translation z comma d, and then finally it's rotation z comma theta. So this is the formula, but eventually it will be a 4 by 4 matrix, right?